Okay, in this lesson, we are going to take our idea of an integral, which is the area under a curve, and a Riemann sum, which we use to estimate that integral, and try to make a perfect estimate. Not an estimate anymore, but the exact amount of volume. And so we're going to look at how that works. So draw a picture of what, just on your own paper, draw a picture of what the integral from 0 to 4 of x squared means. And hopefully you were able to say that, okay, well, this is x squared is the function, y equals x squared. It looks like this. Okay, and it's the area between x equals 0 and x equals 4. So maybe something like this. So it's like this area, okay? And this is up at 16, you know. Okay, so there's our nice labeled graph. This is what the integral from 0 to 4 is. And unlike last class where we had an easy shape like a triangle or a trapezoid or a semicircle that you could find the area of, this is a curve. My picture isn't as curved as it should be, but it is. It's a curve. And finding the area under that curved shape is something that we can't do without calculus. So how do we estimate it? Well, I hope we know that to estimate this area, so we've got this area here, it looks like this. We are going to, it's a right Riemann sum. So we are going to start from the right side. So that's at 4. This is from 0 to 4. And we're going to make rectangles. It says to do it in 4 subintervals of equal length. So to split up 0 to 4 into 4 things, we're going to do 4 divided by 4, because this is 4. We're going to split it into 4 things. And so each of our subintervals will have a length of 1. So it's like total length divided by subintervals. How many subintervals? Okay. So here we go. This is 1, 2, 3, 4. Okay, so we have 4 subintervals of length 1. That is 4 equal subintervals. And now we need the heights of each of these points. Well, how do we find the height at 4? Well, we know the function is y equals x squared, right? So it's y equals x squared. So when x is 4, so f of 4, I guess we should say f of x equals, then we can actually use function notation. F of 4 is 16. 4 squared is 16. So this height is 16. And we can draw a rectangle over, and we draw to the next point, and we make our rectangle. This is going to be an overestimate. It's a right Riemann sum for an increasing function, so that will be an overestimate. And then we'll take our point at 3, and we'll make rectangles there. You need to know what the height is here. What is the height at when x equals 3? The height is 9, because 3 squared is 9. We're doing x squared. That's what the height of the curve is. So go ahead and finish this off on your own and find what the estimate is using a right Riemann sum. And hopefully you saw that we needed the next rectangle would start at 2, and 2 squared is 4. And the last rectangle would start at 1, and 1 squared is 1. And with a right Riemann sum, we don't use the leftmost point, which would be 0 squared, which is 0, but we're not going to use it. So we always start from the right on a right Riemann sum. And these rectangles are going to be a height of 1 times the length of 1, a height of 4 times the length of 1, a height of 9 times the length of 1, and a height of 16 times the length of 1. Multiplying by 1 doesn't do anything, but all of these rectangles had an area, a width of 1. So we got 1 plus 4 plus 9 plus 16, 10, 20, 30. Now, is this an overestimate or an underestimate? This is an estimate. So this is saying the integral from 0 to 4 of x squared is about 30. But we estimated it using a right Riemann sum. Is this an overestimate or an underestimate? And it is an overestimate because when you have an increasing function and you start from the right side, that right side will always be higher, and you'll have this like sections of extra area here. So in fact, this isn't a particularly good estimate. There's a button in the calculator that can do the integral, and I'll be showing you more about this later in the year. It's FN int. You press math if you want to know now. You press math, and you go to fn int, and you say we want the integral from 0 to 4 of x squared, and we need dx to end the integral. We'll learn about this later. This isn't me telling you, you need to know this already. And the real area is 21.333. Is this a good estimate? I mean, it's kind of close to 21, but it's not particularly good. So our next question is, how could you still use a right Riemann sum? Like if we used a trapezoid rule on this, it would be better. We'd get a better estimate. In fact, go ahead and find the estimate using a trapezoid rule. Using 4 subintervals of equal length from 0 to 4, estimate the integral from 0 to 4 of x squared using trapezoid rule. Hopefully here you saw that it would be the left side is 0. So now we do have to use this leftmost point. It would be 0 plus 1. We have to take those and average them together, divided by 2 times a width of 1. Then we take 1 and 4, and we average them together, multiply by the width of 1. We're going to do 4 and 9, average them together, and multiply by a width of 1. And then last, we're going to do 9 plus 16, and multiply them by 1. And so I bet this will be much closer to the real answer. Let's see, 1 half plus 5 halves plus 13 halves. I'm just adding these together. It's 13 halves plus 25 halves, 22. I mean, that is a way better estimate. So the trapezoid rule, I mean, is such a better estimate. As you can see, I mean, like, just look at how this looks. If you're doing x squared and you do the trapezoid rule, you know, this is what our estimate looks like. And it's a slight overestimate, but it's not far off. Like, this is just a way better estimate if we make trapezoids. But that's not what we're going to be about today. How could you use a right Riemann sum? We used a right Riemann sum and we got 30. How could you use a right Riemann sum to get a better estimate of this integral? And the trick is, we could get a better estimate if instead of having 4 subintervals, which has, look at that huge overestimate. What if we made more subintervals that were off by less? For instance, I could do 100 subintervals. What if we do like 100 subintervals? Well, now, like, you're getting really close to the right answer. And so let's look at how you would find that area. Well, we would add up a whole bunch of rectangles. There would be 100 rectangles to add up. And so before we get into like how we would write this, I want to show you some notation that you might or might not know from pre-calculus or before. I'm not sure if you're familiar with this. This is summation notation, or sometimes it's called sigma notation. This letter is called a sigma. It's a Greek letter. And this tells you how to add up a bunch of things. So this says the sum of different f's, and you'll notice there's this index I, where I goes from 1 until n. So I goes from 1 to n. And what it means is you're going to start, there's like some function of I, and you start it with 1, and then you do 2, and then you do 3, and then you do 4, and then you keep going until I gets up to n. Okay? So it's a way of adding things up. For instance, let's say I did the sum of I from I equals 1 to 5 of 2i. Okay, this is saying I is going to go from 1 to 5. So it's going to be 2 times 1 plus 2 times 2 plus 2 times 3 plus 2 times 4 plus 2 times 5. And I believe this is 30. But it's a shorter way, like this is way shorter than writing this, especially when you start adding up more and more things. So let's look at how we could have written this sum up above that we already did. There were 4 subintervals, so we're going to put the sum from I equals 1 until 4 of I squared times So we were finding the length times the width of these rectangles, and this was I squared times, we took this was the length of the rectangle, so it'll be like 1 squared, 2 squared, 3 squared, and 4 squared. And we multiplied it times whatever the width of the rectangles were, which we had this whole length of 4 divided by 4 because we split it into 4 subintervals. And so this was 1, and so we end up with I equals 1. It's 1 squared. This is just 1, and it's going to go away. 1 times anything is 1. 1 squared plus when I is 2, this will be 2 squared, plus when I is 3, this is 3 squared. And when I is 4, this is 4 squared. This is exactly what we had before. 1 plus 4 plus 9 plus 16. But it's going to be super useful for doing it when we have like 100. So we're going to have 100 rectangles. We're going to add up 100 rectangles. We're going to start from I equals 1, and we're going to go to what? We're going to go to 100. Now, what are it's going to be, we're adding up the area of these rectangles, and rectangles are length times width. And so let's start with the width. The width of each of these rectangles, how can we find it? Well, we know that this total length goes from 0 to 4. This is a length of 4. But we have split the 4 into 100 pieces. So we're going to take 4 and split it into 100 parts. That's what the length of each of these rectangles, the width of each of these rectangles will be. It will be 4 split into 100 parts. They'll all be 0.04. Because if you do 0.04 plus 0.04 plus 0.04 100 times, which is 0.04 times 100, that will be a length of 4. So the width of each of these rectangles, if there are 100 of them, will be 0.04. And what is the height of each one of these rectangles? Well, it's going to be based on the ith rectangle. So we're going to figure out it's going to be something squared, but the question is, what is it squared? And what it's going to be is it's going to be the distance between here, we're going to separate it. It's going to be 4 over 100 again times I. Because the first rectangle will be 0.04 squared. The next rectangle will be 0.04 times 2, which is 0.08 squared. Then 0.04 times 3 squared, which is 0.12 squared. And that will be the height of each of these rectangles. And by the time we get to 100, you'll notice that 100 times divided by 100, so 4 over 100 times 100. So when I is 100, 4 over 100 times 100 will be 4, and that will give us the height of the last rectangle, which will be 4 squared. So this is the height of each rectangle times the width of each rectangle, or length times width, either way you want to call it. And the height, the width, is going to be how wide this was divided into that many parts, times the height, which will be, we'll use this function, f of x equals x squared, but what will the x be as we go along? Well, it'll be the width of each rectangle times which one are we on. That's how far over we'll do when we'll square it. So there's actually a button to do sums in the calculator, and it might take this a little. I'm not sure how well it'll do it. So summation from, I'll put x equals 1 to 100 of, this is, what do we say? This was 4 over x. 4 over 100 times x squared. Oh, wait, hold on. Oh, no. This needs to be within the summation. I needed a parentheses. Sorry, this is not something, you're not going to need to do a lot of summations this year. The next calculus course is going to deal with them a lot, but that needed to be inside of the sum. Otherwise, it would be like wrong order of operation. So the calculator's thinking for a while. It's actually coming up with hundreds of areas of rectangles, and it's like multiplying them all out. So it's doing a ton of calculations here, and there it is, 21.654. Now, is that the exact right area? No, this was just an estimate. Remember, the exact right answer when we looked it up was, we did it in the calculator, we found the integral using the calculator, it was 21.333. But when we use a smaller subinterval, we could get it much closer. Now, how could we get an even closer estimate? Well, what if instead of 100 rectangles, what if we used 1,000 rectangles? If we use 1,000 rectangles, we'll need to do the sum from 1 to 1,000. We'll take that length of 4, and divide it into 1,000 parts. And the height of each rectangle is going to be, we'll take 4 and split it into 1,000 parts and go over by that much each rectangle and square it. And this will take the calculator a while to get, but I bet, you know what my bet is? My bet is it'll come out to be like 21.3654 or something. That's just a guess. But I bet it comes really close to 21.33333, and this is my guess for how it's going to look. I bet it's this one. We'll give it some time to work. In the meantime, let's talk about integrals. We can get the exact integral by doing a limit. The integral from a to b of f of x, if f of x is integral, then we can do the limit of rectangles. This is the width times the height. So if there's some function, we can say, well, what is it changing by each time? And what it's going to be changing by is always going to be b minus a. That's the length from a to b. So what's going on here is, you got some function and we want to find the integral from a to b. Well, the width between here and here, how wide this is b minus a, right? This one minus this one. That's how wide it is. But we're going to divide it into n rectangles. This is the number of rectangles. And so we're going to divide it into n rectangles. That's going to be the width of each rectangle. So however many rectangles it is, we divide it into that many rectangles. And we're going to multiply that times the function. So it's f of what x are you at for each function. And what it's going to be is I wish I had left myself some more room here. I'm going to write this over here, guys. I'm sorry. This is going to be f of, we're going to plug into the function, the starting x value, which is a, plus the width of each rectangle, which is b over a, b minus a divided by n. Oh no, you guys haven't been able to see this. This is so terrible. I'm so sorry. Guys, the width of each rectangle is b minus a over n. And the height of each rectangle is going to be whatever the function is. Remember how we plugged in x into x squared to find the heights there? We're going to plug this into the function. And what we're going to plug in is our starting x value is going to be a, that's the lowest x value, plus whatever the width of the rectangle is, times I. And sometimes this will be written as f of a plus b minus a times I up here over n. And you'll see how this works in just a second. We're going to do an infinite limit, and it will find the exact area. By the way, the calculator finished this. It was 21.365, although it wasn't a 4. It was 3.4. I guessed wrong slightly, but I was pretty close guess. So look, it's getting closer to 21.333. And in fact, we are doing a limit as x is going to infinity. We're putting more and more rectangles in. And each time we put in more rectangles, the width of the rectangle is getting smaller, but there are more rectangles, and it finds a closer and closer estimate of the real one. And as we do the limit as x goes to infinity, you'll get the exact right answer, because what's happening is you're basically like putting in lines, right? Like oh man, you guys could see it. You're putting in like infinitely small rectangles, and that will find the exact area of whatever is there, because there won't be space in between them. So let's see how we would write an infinite Riemann sum here. By the way, infinite sums is a really important topic in the next calculus class. So the second semester of calculus, the second calculus course involves infinite sums, and you'll do a lot more with these infinite sums. Today, you don't need to get this at a super high level for AB calculus, but you do need to get it at least a little bit to get a couple of, there's only going to be like one question on this on the AP calculus test. This will be like, today's lesson is going to be one question on the calculus test. So this will be, to find this integral, it will be the limit as n goes to infinity of the sum from I equals 1 to n. So we're going to be summing up n rectangles, and we want this number of rectangles to go to infinity of, it's going to be length times width, or height times width. And the width is going to be 4 over however many rectangles. We're going to take that length of 4 because it's 4 minus 0. So 4 minus 0 is how much spread there was here, right? And we're going to divide it into n rectangles. And as n goes towards infinity, this width is going to be going towards 0. The height of each rectangle, we're going to be squaring numbers at different places, right? That's the height is we're going to be doing x squared. The question is just what is x squared? And it's going to start at 0. So it's going to be 0 plus. We don't have to put the 0 plus, but we could if we want. 0 plus the width of each rectangle, which is 4 over n times I. Okay? And we're going to square that. So whatever x value we're at for the rectangle, we're going to square it because that's what the function was. That's how we find the height of x squared, right? You plug in the x into x squared, and you get this. This could be simplified a little bit. I equals 1 to n of 0 plus something doesn't matter. And you can multiply the I on top. So sometimes we'll put 4i over n squared times 4 over n. So this would be like the simplified version of this infinite limit. Oh, we need the limit as n goes to infinity. So you'll notice when n was 4, we got a width of 1, and it was just 1 squared, 2 squared, 3 squared, 4 squared, right? Because 4 divided by 4 canceled out. When we had a width of 100, when we had 100 rectangles, it was dividing by 100. The calculator is still thinking, by the way, on this 10,000 rectangles it's trying to add up. It might be going for a while. Okay, let's see how we can do on this one. So this is the integral from 5 to 8 of square root of x plus 3. So we're always going to do the limit as n goes to infinity of the sum from I equals 1 to n. This will always be the same no matter what the function is. Notice this is the exact same as it was before. This is saying we're adding up infinite rectangles. What happens if we add up more and more and more and more rectangles? Okay. Now the width, what is the width here? The width is going to be 8 minus 5 divided by n. We need to divide 8 minus 5, that's a length of 3 into n parts. So we're going to put 3 over n in a second when we simplify. And what is the function going to be? Instead of squaring, like before we had squaring, this one is going to be square root. And when we plug it, what are we plugging in for x each time? Well, the lowest x is going to be 5 because that's where the integral starts, plus the width of the rectangle, which was 3 over n times I. Okay, that's what x is going to be. 5 plus 3 over n times I. And then there's this plus 3 part. That doesn't have an x with it, so it's just plus 3. Now, I'd like to point out that when you get to n, you can see that you'll be at the end of your integral. Like here, when I is equal to n, when we get to our last rectangle, multiplying by n and dividing by n will cancel out, and all that will be left is 3. And 5 plus 3 will be 8, and that'll be the end of the integral. Same thing happened over here. When I is equal to n, multiplying by n and dividing by n cancel out, and all that's left is 4, and that's the end of the integral, 4. 0 plus 4 is 4. This can be simplified a little bit. So it's the limit as n goes to infinity of the sum from I equals 1 to n of 5 and 3 can be combined, and the I can go on top. So 3i over n times, this is just 3 over n. So this is our infinite limit. Cool. All right, let's see how you guys can do on your own here. This is, so what do we write at the beginning? We write the limit as n goes to infinity of the sum from I equals 1 to n. That's always going to be the beginning of our limit. And it's the sum of, okay, so what's the width of the rectangle going to be? Well, it's going to be 5 over n. And the way I got that is I did 2 minus negative 3. This is 5. And that's because the distance between -3 and 2, this distance is 5. That's like how long this length is, and we're going to split it up into n rectangles, right? However many rectangles that is. So we're going to divide it into n parts. Okay. Now, oh man, I did not leave myself enough room here. Okay, so this is going to be multiplying times this thing I'm going to write down here. Where are we going to be at for each rectangle? Each x, every time there's an x, I'm going to plug in where we are for each rectangle. And we start at the beginning of the integral. So -3 plus the width of each integral, the width of each rectangle times I. So basically this moves us over. Every time I goes up by 1, we move over by 1 width of the rectangle. So this is our x cubed. Again, notice that when I equals n, multiplying by n and dividing by n will cancel out, and we'll just get -3 plus 5, and we'll be at 2. We'll be at the end of the integral. So when we get all the way to our last rectangle, we'll be at getting the height of that last rectangle, and it'll be at the end of the integral. When I is at 1, you're basically at the start of the integral at -3. Okay, so there's our first one. Minus 5 times the x is going to be -3 plus 5 over n times I squared. So here's our x cubed minus 5x squared. And that 8 doesn't have an x that's getting plugged in. So this whole thing is the length. This is our f of x sub I. So at different x's, what is the function value? Well, the function value is going to be at this at different i's, at different places on the rectangle. All right, let's practice this sum. Let's see how you guys can do on a few of these. And let's see. How about this? Now we want to write an equivalent integral. And it turns out there's actually more than one possible integral for these that have the same area, and that's okay. We just need to find one. So the first thing we're going to look at is we're going to look at what is the width of the integral. So what is the width of this integral going to be? So it's going to be the integral from a to b. We want to know what b minus a is equal to. What is the width of this integral? And we can see that it's 3 by whatever it's being divided by n, right? So here's the width. Here's that width being multiplied by I each time. There's that width being multiplied by I again. Now, what is the integral from? Well, I don't see any like 5 plus something here. And so this is just going to be the integral from 0 to 3. I can tell that because I don't have any, if this had been like 2 plus 3i over n, then maybe it would be the integral from, this would be the starting amount from 2 to 5. It would still need a width of 3, but because there's no plus anything, I know it's from 0 to 3. So it has a width of 3. And what is the function? Well, I can see what's happening here, right? The function is being cubed, so I need an x cubed. This is like my x. What's the last part? Well, it's minus 6x. This is, again, my x here, 6x dx. So this is the integral that is the same as this infinite sum. Okay? All right. How about this one? What is the width of this integral? The width is 2. And there are actually 2 possible integrals you might write here. I want you to try to write the integral yourself, and then I want to show you the 2 possible integrals this might be. One possible integral this could be is it's the integral from 0 to 2 of, clearly this is the square root of, here's my x, plus 5. That is a correct integral. But it turns out you could also have said, hey, you know what? This plus 5 is where the integral starts. And in that case, it would be the integral from 5 to 7, because it has a width of 2. So 5 to 7 of the square root of just x, because this x would start at 5. Both of these are correct. And oh man, the calculator still, I don't really want to interrupt the calculator, but I'm going to. So it turns out infinite sums, the calculator has a hard time finishing. So I'm just going to quit and break it because I want to show you instead something that it can do kind of quickly. Let's look at square root of x plus 5 and square root of x. And we're going to graph it. And here's square root of x plus 5. And we're going to do the integral from 0 to 2, there's that integral. It's, this is approximately equal to, this is 4.893 about, okay? We go to 3 decimal places in calculus. Let's go to the other function. What about the other function? Let's do the integral on this function from 5 to 7. And it's the exact same area. This area is also 4.893. So there's 2 ways to look at it. And honestly, this is probably going to come up on the multiple choice section. And so you want to be able to recognize either one of these. So this could either be the start of the integral, or it could be the width of the integral. All right, guys, try this one on your own. This one's written slightly different, but it's okay. What is this integral? And hopefully you saw that instead of having the times 5 over n, this got factored out to the outside this time. And that's okay because it's independent of I, so you can factor it outside of the sum. It's like factoring out a common factor. All of them are getting multiplied by the same width. And we talked about last class how if they all have the same width, you can factor it out to the outside, and it makes it go a little bit faster. And in fact, if I had done that in the calculator when I was doing this sum, so let's go back up here. So I'm going to come up here, and I'm going to delete this 4 over 1,000. Oops. And we're going to put 4 over 1,000. We're going to factor it out. Okay, 4 over 1,000. And we're going to factor it out to the outside, and it'll make the calculator's calculations go a lot faster. Because instead of like multiplying by 4 over 1,000 every time, it's only multiplying by 4 over 1,000 once at the end, which, you know, will be a lot fewer operations. It'll make it go much faster. Okay, where were we? Okay, so this has a width of 5. And so I don't see any plus anything, so it's probably going to be the integral from 0 to 5 of, here's our x. So this is 5e to the x dx. This is our integral. So it had a width of 5, and this 5 is not part of the x. It's just 5 times e to the x. So we needed there. With that in mind, what do you think this is the integral of? The integral from what to what? The integral from, and I think this is most reasonable. I really see this 4 plus x here. So this is going to be the integral from 4 to what? Well, I see that this has a width of 2. So width of 2. And I can see that here also. There's a width of 2. So the integral from 4 to 6 of, what's my function? Well, here's a 3. And here's my x squared minus, this is just x, 3x squared minus x dx. Okay. The calculator got that a lot faster with the 4 over 1,000 factored out to the outside. Okay. Here is a cool one. You guys do not know how to do infinite sums, although you will learn it next class, the next calculus course you would take. You would learn how to do this infinite sum. But for now, let's talk about how to do this infinite sum. Well, you don't know how to do this infinite sum, but we know how to change it into an integral. We want to find the value of this infinite sum. And we're going to change it into an integral. What integral is this? This is the integral from, looks like it starts at 2 and has a width of 4. So 2 plus 4 is 6. So the integral from 2 to 6 of, oh no, we can't do the integral from 2 to 6 here. I was wrong, guys. The reason is the 6 is multiplying here. So this has to be the integral from 0 to 4. Sorry, the width is 4. The integral from 0 to 4 of 2 plus 6x. The reason that the 2 isn't adding with this, the x would have, if this had been 2 plus 4i over n here, then it could be the integral from 2 to 6. But because the 2 is not where the x is, like the 2 has to be separate. So 2 plus 6x. Okay? So how does this help us? Well, this is an integral you know how to do geometrically. Use your skills from 2 classes ago to find this integral. This is just a graph of 2 plus 6x. So the y-intercept is 2. It has a slope of 6. from 0 to 4. So when x equals 4, 6 times 4 is 24. 24 plus 2 is 26. So this will have a height of 26. And this is a trapezoid. So we can find the area of this using some geometry. This is the height is 2 here because that was the y-intercept. 2 plus 26 divided by 2 times the height of the trapezoid is 4. So 28 divided by 2 is 7. 7 times 4 is 28. Notice that if I tried to do this infinite sum, okay, look, this is 4 over 1,000 again. So 1,000 rectangles, 4 over 1,000. Let's actually clear this. So 4 over 1,000 times the sum from I equals or x equals 1. We usually use x in the calculator to 1,000, but everywhere else we use I or n of, what would this be? This was 2 plus 6 times 4x over 1,000. That's the width. Times, oh, shoot, we already factored out the 4 over 1,000. Okay, good. So this calculator is going to do 1,000 rectangles, and it's going to take it way longer than if we just changed it to an integral. Uh-oh, something's wrong. Did I mess something up? 28 over 4. What did I do wrong here? Or did I do something wrong here? 4 over 1,000 times... Something's wrong. Where's my error? 0 to 4, 26. This divided by 2. Oh, this isn't 7. 2 plus 26 divided by 2 is 14. 14 times 4 is 56, which is very close to this 1,000 rectangle one. This is the exact answer, and this is the estimate. So you do have to be able to turn an infinite sum into an integral, because you can then do that integral. And in fact, we'll learn more integral tricks over the next few days of how to, next unit about how to do integrals of curved things. And so we'll be able to do infinite sums in that way. It's really nice. Okay. So it turns out we've been using a right Riemann sum, but you could use a left Riemann sum instead. It turns out if you split an infinite number of rectangles, it doesn't matter if you start from the right or the left, because it's like 0 area you're losing if you start on the right or the left. They both converge to the exact right answer. If we do a left Riemann sum, we won't use that last value, and instead we'll use the first value. And so the way we would do this is still the limit as n goes to infinity, but instead of starting at I equals 1 and going to n, we would go from I equals 0 to n minus 1. You just wouldn't quite go to n, you would stop 1 before it. Same thing, it's going to be 4 over n, that's the width, times the length is again going to be your x squared, so 4 over n times I. So almost the exact same thing. You would just start at 0 instead of 1, and it comes out to be the exact same estimate because you're doing the limit as n goes to infinity. It doesn't matter whether you take that first rectangle or the last rectangle. They both come out the same. Using a midpoint, I just want to show you this so you can like recognize it, so you're not like, hey, why is it going from 0 to whatever? Using a midpoint Riemann sum, sorry, this wasn't the infinite one. The infinite one was down here. This is, it said using 4 subintervals. So now here's x squared. We start on the left. So 0 squared, 1 squared, 2 squared, and our last rectangle will be 3 squared. So I'm sorry, I should have put 9 there and 4 there. And we won't use the 16. So when we start from the left, it's 0 squared plus 1 squared plus 2 squared plus 3 squared, but we don't use the far right point. And you can see that the I starts at 0 and goes to 1 lower than n, as I was saying there. But the widths are still 1 in this case. 4 divided by 4 is 1. And you can see that it just starts at 0. That's the only difference. If we did a midpoint Riemann sum with 2 subintervals, go ahead and estimate what that would be. So hopefully you know with a midpoint Riemann sum we would not use 0. We would use 1, and we would go both directions. We would not use 2. We would use 3, and we would go both directions. And we would not use 4. So we don't use 0, 4, or 2 when we're using the midpoint Riemann sum. And this time they have a width of 2 instead of a width of 4. So this would be 1 times 2, and the height here would be 9. 9 times 2, and this comes out to be 20, which is way closer than the right or the left Riemann sum comes out to be. This comes out to be 9. This is 14. That's way too low. When we did the right Riemann sum, it was way too high, and this is actually pretty close to 21.33333. How about using a trapezoid rule? We already did that. We did the integral from 0 to 1. We did, so it's 0 plus 1 divided by 2. You can do it on your own here. Plus 1 plus 2, 1 plus 4 divided by 2, plus 4 plus 9 divided by 2, plus 9 plus 16 divided by 2. And I believe, what did we say this came out to be before? It was, I don't remember what it came out to be. We calculated this earlier. I forgot I was going to be doing this later. It came out to be 22. So these are both pretty close to the real answer of 21.33333 repeating, right? But, you know, this was the best, this was the second best, and the other ones weren't very good. In infinite Riemann sum, we can also write. But I think we're going to stop there for today, guys. This is good enough for what we need. I hope you guys are feeling okay about this, having practiced it some. This is a very low-level tested skill on the AP exam. If you can recognize, like it's almost always multiple choice, if you can take, if you can take a Riemann sum and pick which one of the integrals it is, you're in great shape. So that's what you'll practice tonight. You'll have a multiple choice version of it where you have to match it up. All right, guys, I hope you have a good rest of your day, and I'll see you next class.